Hello and welcome to Meduhub. I am Neha Gupta from your chemistry faculty, and today we are going to be talking about aldehydes and ketones. Aldehydes and ketones are a class of organic compounds in which there is a carbonyl group present. The carbonyl group is also called the oxo group. In a carbonyl group, we have a carbonyl carbon, that is a carbon which is doubly bonded to an oxygen, and it is flanked by two groups here. In the case of aldehydes, one of these R groups is a hydrogen atom. So this means that out of the 4 valencies of carbon, one of the valency is satisfied by a hydrogen atom, which means that the aldehyde group, which can be written as CHO also, is always at the terminal end of a chain. So it is at the end of a chain. Whereas in a ketone, the carbonyl carbon is flanked by alkyl or aryl groups on both the sides. Alkyl or aryl. So this means that a keto group will always be in the middle of a chain. In today's video, we are going to be covering the properties, the general properties of aldehydes and ketones, their structure and their methods of preparation, and of course their nomenclature. This will be a 2-part video. In the second part, we will be covering all the reactions of aldehydes and ketones. So let us move forward. So this is what aldehydes and ketones are. They contain a carbonyl carbon. Now let us see how they are named. If we talk about aldehydes, the common name of the aldehydes are derived from the name of the carboxylic acid which they form upon oxidation. So take this example here. The common name of this carboxylic acid which contains one carbon atom is formic acid, HCOOH. Now the aldehyde from which it is derived is HCHO. So what happens? We drop the I and C of the formic acid and we add aldehyde to it. So HCHO will be called formaldehyde. Formaldehyde. This will be the common name of this aldehyde, the simplest of the aldehydes, which contains one carbon atom. Look at this one now. This aldehyde, which is a 4 which has a 4 carbon group attached to the CHO group here, is formed from isobutyric acid. So drop the I and C of the isobutyric acid. What will be the common name of this aldehyde? Isobutyraldehyde. Similarly, if you see here, CH3COOH, this is acetic acid. From acetic acid, the aldehyde that can be reduced and formed is CH3CHO. This aldehyde is called acetaldehyde. Acetaldehyde can be formed by dropping the I and C of acetic and adding the word aldehyde to it. Now look here, if there are substituents, like in this molecule here, we have an aldehyde group CHO, then we have a hydroxy substituent here. In the common system of nomenclature, you start numbering the carbons as alpha, beta and gamma. The alpha carbon will be the carbon that is directly attached to this aldehyde group here. So this carbon is alpha, this is beta and this would be gamma. To the beta carbon, a hydroxy group is attached. So this will be beta hydroxy. And what will be the common name of an aldehyde which contains 4 carbon in a chain? This will be butyraldehyde. So beta hydroxy butyraldehyde. Look at this example here. We have a benzene ring to which a CHO group is attached. This is the simplest of an aromatic aldehyde. This is called benzaldehyde. Benzaldehyde is the accepted common as well as the IUPAC name of this simplest aromatic aldehyde. Now let us see the IUPAC names. IUPAC names of aldehydes are written by adding the suffix al, al, to the alkyl group from the alkene from which they are derived. So here there is one carbon only, so this will be methane. Drop the E of methane and add al. This will be called methanol. So what happens? You see the number of carbon atoms in the chain. You see which alkane it is derived from. Drop the E of that alkane and add al as a suffix to it. This gives you the IUPAC name of this aldehyde. Coming here, now this has two carbons, CH3CHO. This is derived from ethane. So the aldehyde will be called ethanol. Look at the third example here. The basic carbon chain here is this one, containing 3 carbons. Now there is a methoxy group as a substituent here. So for that you will have to number. Now in the IUPAC system of nomenclature, numbering starts from the carbon which contains the carbonyl group. So this is carbon 1, this is carbon 2, this is carbon 3. So this will be 2-methoxy. Since there is a methoxy group at second carbon, 2-methoxy, and there are 3 carbons derived from propane, so this will be propanol. Propanol. 3-methoxy propanol. Look at this example here now. See the longest carbon chain, 1, 2, 3, 4, 5. Now there is a double bond between carbon 2 and carbon 3 here, and this is a 5 carbon chain. So this is a pentene. The pentene has an aldehyde group at the first carbon. So this will be pent. Specify the position of the double bond. 2 ene 1 al. So you drop the E of the pentene and add al. So that is pent 2 ene 1 al. If the aldehyde group is at the first carbon only, obviously, so we can drop this one as well because it is implied that the aldehyde will be at the terminal carbon, and we start numbering always from the carbon which contains the carbonyl group. So this one can be dropped. We can just write pent 2 ene al. Alright. Now this example here. Here you will see that there are 3 aldehyde groups. Okay, now all 3 of these have to be given equal priority. So we will just number the carbon in the chain here, 1, 2, 3. So this is propane, 1, 2, 3, tricarbaldehyde. Okay. Now let's see some cyclic aldehydes. How do you name cyclic aldehydes? For the nomenclature of a cyclic aldehyde, you will first see the cycloalkane to which an aldehyde group is attached. So this is a cyclohexane. To cyclohexane, now you will add a word that is carbaldehyde. So the name of this one will be cyclohexane carbaldehyde. Carbaldehyde. What happens if there is a substituent here? Like in this case, this is a cyclopentane, a 5 carbon ring, and an aldehyde group is attached here, and here to this carbon a hydroxy substituent is attached. Here the numbering starts from the carbon to which the aldehyde group is attached. So this will be carbon 1, this will be carbon 2, 3, 4, 5. So this is a cyclopentane. To the second carbon in cyclopentane, a hydroxy group is attached, and hence this will be called 2-hydroxy cyclopentane. And because to the first carbon an aldehyde group is attached, we will write carbaldehyde. 2-hydroxycyclopentane carbaldehyde. What about some aromatic aldehydes? You know that the simplest of the aromatic aldehydes is a benzaldehyde. So this is carbon 1, 2, 3 and 4. At the fourth carbon, OCH3 group is attached. So this will be 4-methoxy benzaldehyde. Benzaldehyde. Here, this is the common name of this compound is vanillin. This is obtained from vanilla beans. The smell you get when you smell vanilla beans, vanilla ice cream or vanilla essence that you add in cakes, it is because of this benzaldehyde here. So, the aldehyde group is at this carbon. So, this will be carbon 1, 2, 3 and 4. This will be a methoxy group. This will be a hydroxy group. So, it will be called 4-hydroxy 3-methoxy benzaldehyde. Now, what about ketones? Ketones have two alkyl or aryl groups on both sides of the carbonyl carbon. So, either both the alkyl or the aryl groups can be same or they will be different. If they are same, they are called simple ethers. If they are not same, it's called a mixed ketone. So, if there are two different groups, it's a mixed ketone. If there are two same groups, it's called a simple ketone. So, this one is a simple ketone here, and the common name of this would be dimethyl ketone. So, what do? You write the name of the alkyl group separately, alphabetically, and then you add the word ketone to it. Looking here, we have an ethyl group here, and this group is an isopropyl group. So, this will be a mixed ketone. This will be called ethyl space isopropyl ketone. Coming here, this is the carbonyl group. On one side it is flanked by a methyl group, on the other side it has a phenyl group. This is also called acetophenone, but the other common name of this would be methyl space phenyl space ketone. This last example here is propiophenone. Here you see the carbonyl group has a benzene ring on one side and it has a CH2 CH3 group on the other side. So this will be ethyl phenyl ketone. So this is for the common names of ketones. What about the okay, we'll take two more examples for common names. Look at this compound here. If there are substituents in a ketone, since ketone has an alkyl group on both the sides, one side the substituents are numbered as alpha beta and on the other side they are numbered as alpha dash beta dash. Now look at this one here. If the chlorine substituents were not there, so this would mean that there is an ethyl group on both the sides, 2 carbon each side. So this will be a diethyl ketone, but it has a chlorine group here on the beta carbon and a chlorine group here on the beta dash carbon. So this means it is beta comma beta dash dichloro diethyl ketone. And this is a cyclic ketone. Now the difference between cyclic aldehydes and cyclic ketones is that in a cyclic aldehyde, the CHO group or the aldehyde group will always be attached to one carbon of the ring. So if we have a cyclohexane, the CHO group will be outside the ring. But since in a ketone, both the valencies of the carbon are satisfied by 2 more carbons, the keto group will be inside the ring here. So this carbon will be the carbon to which the carbonyl group is attached. C double bond O. Now for the common nomenclature of such ketones, what do? The carbon next to the carbonyl carbon, just like here, is given the name alpha. So we have a methyl group. This will be alpha methyl, and this is a cyclohexanone. Now about the IUPAC nomenclature. In IUPAC nomenclature, what do? You add the suffix -one, O-N-E, to the name of the alkene from which the ketone is derived. So here you will see there are 1, 2, 3, 4, 5 carbons. You will start numbering the carbon atoms from the end where the carbonyl group gets the lowest possible number. So this will be carbon 1, carbon 2, 3, 4 and 5. This is a pentanone and it has the carbonyl group at the second carbon. So this will be pentane 2-one. Looking at this example now, 1, 2, 3, 4, 5. It is a 5 carbon chain. There are 2 methyl substituents here. We will start numbering 1, 2, 3, 4, 5. So 2, 4 have dimethyl substituents. 2, 4 dimethyl. 5 carbon chain, so it's a pentane. Pentane, drop the E of the pentane. At the third one we have a keto group. So it is 2,4 dimethyl pentane 3-one. Okay. So this is it for the nomenclature. Now let us see what is the structure of a carbonyl compound. So we have carbon double bond oxygen and 2 bonds here. This can either be a hydrogen or an alkyl group or an aryl group. In a carbonyl compound, there are 3 sigma bonds because this carbon is sp3 hybridized. Alright, sp2 hybridized. This is sp2 hybridized. It will have 3 sigma bonds and it will be a planar structure, which means that these bonds will be 120 degrees. Now the fourth carbon, the fourth electron of this carbon remains in the p orbital, which forms a pi bond with the electron of oxygen here, which is the pi bond. So a carbonyl compound will have 3 sigma bonds, 1 pi bond which is formed by sideways overlap of the p orbitals. Apart from this, the oxygen has 2 lone pairs as well. So this is the structure of carbonyl compounds. Now this bond is polar due to the high electronegativity of oxygen. But the dipole moment measurements that have been found, the values of these are much higher than what would be expected if it is just the inductive effect of this oxygen atom. That is because the carbonyl group is a resonance hybrid of this, a neutral molecule and a dipolar molecule. It is due to the contribution of this dipolar resonating structure that you see that the dipole moment of a carbonyl carbon here with this oxygen atom is very high than a value that will be predicted only if you take into account the minus I effect of this oxygen atom here. Okay, so now that this carbon has a positive charge, it means that this carbon would be an electrophilic center. And because it's an electrophilic center, it will be susceptible to attacks by a nucleophile which would be an electron-rich species. So this carbon is an electrophilic center and it acts as a Lewis acid, whereas the oxygen is readily able to accept protons due to the negative charge here. This can easily take up a proton and become an oxonium ion. So we have a carbonyl compound here which takes up a proton and gives us this OH positive charge here. This can be a resonance hybrid of this contributing structure. Now look at these two structures here. We understood that this carbon is an electrophilic center. This oxygen can easily take up a proton. So this is acting as a Lewis base and forming an oxonium ion. Now this means that in the presence of an acid, what is happening, since this oxygen is getting protonated, this carbon now in this contributing structure here gets a positive charge. So it means that if a nucleophile gets added on to a carbonyl group in the presence of an acid, the nucleophilic addition reaction to this carbon is catalyzed by an acid. So in the presence of an acid, the nucleophilicity of this carbon increases and hence the nucleophilic addition reactions are acid catalyzed. So let us see what happens when a nucleophile gets added. Addition reaction. So this is the carbonyl compound R dash double bond O. We have HZ, where Z is the nucleophilic part containing the negative charge, and we have a proton H plus. When HZ reacts with the carbonyl compound, it gets added on to the carbonyl carbon, giving us this product R dash OH and Z. So this is the addition product. Now look at this carbon here. This carbon is tetravalent now. Initially, all four valencies are satisfied by different groups here. Here it is sp2 hybridized. Now the hybridization after the addition reaction has changed to sp3. So this obviously means that there is increased crowding around the carbon atom. Here only 3 groups are attached, 1 oxygen atom and 2 R and R dash groups. When a nucleophile attacks, we have now 4 groups here, R, R dash, OH and Z. If we compare the nucleophilic addition reactions of aldehydes and ketones, what will you see? That in aldehydes, one of the R groups is a hydrogen atom, whereas in ketones, both the R groups are alkyl groups. So as the size of these alkyl groups increase, the steric hindrance increases, and hence you would find that in the case of aldehydes, the reaction is faster and this equilibrium is also attained faster compared to ketones. So we can say that ketones are less reactive than aldehydes. Less reactive than aldehydes due to steric reasons. That is, if another group gets attached to this carbonyl carbon, there will be too much crowding around this, and if the size of the alkyl groups is greater, then the reaction would not achieve equilibrium that much faster as it would in an aldehyde, where one of the R groups is just a hydrogen atom. There is another reason due to which we can say that ketones are less reactive or aldehydes are more reactive towards nucleophilic addition reactions, and that is the electronic effect or the inductive effect. Inductive effect. So due to the strong minus I effect, just a second, sorry. So let me draw the carbonyl carbon and the two R groups. In the case of an aldehyde, since one of the R groups is hydrogen, only this R group has a strong plus I effect here. What happens due to the plus I effect of this alkyl group? The positive charge on this carbonyl carbon, which is due to the resonance, positive and negative, is somewhat redistributed or it is diffused between these carbons. Because this has a strong plus I effect, it pushes its electrons towards this carbon, and hence this positive charge is nullified to some extent. In the case of ketones, this effect is doubled because there are two alkyl groups now and both of them have a plus I effect. Because of this, the positive charge on this carbon is nullified to a much larger extent compared to aldehyde. So because of the inductive effects of the two alkyl groups in a ketone, we can again say that aldehydes are more reactive towards nucleophilic addition reactions. Right? So there are two reasons. One is overcrowding or steric effect, other one is the inductive effect or the electronic effect. So this is it for the structure and how it affects the reactivity of aldehydes and ketones. Now let us see some general properties. General properties of aldehydes and ketones. If we talk about HCHO or methanol, it is a gas at room temperature. And if we talk about ethanol, it is a volatile liquid at room temperature. All the other aldehydes and ketones are either liquids or solids at room temperature. If we talk about their boiling points, you will see that if we compare their boiling points to hydrocarbons or ethers of similar molecular mass, aldehydes and ketones will always have a higher boiling point. This is because of the dipole moment that is present. Since this bond is dipolar, there are dipole-dipole interactions. Dipole-dipole interactions existing between molecules of aldehydes or ketones, which makes their boiling point higher compared to hydrocarbons or ethers, which only have weak van der Waals forces of attraction between them. But if we compare the boiling point to alcohols, which have an OH group of similar molecular mass, we'll see that because alcohols have intermolecular hydrogen bonding, which is a stronger force of attraction compared to dipole-dipole interactions, the boiling point of aldehydes and ketones when compared to alcohols will always be lower than alcohols. If we talk about the miscibility in water, lower aldehydes like HCHO or CH3CHO or acetone CH3COCH3, which is the simplest ketone there is, because a ketone has a carbonyl group flanked by carbon. So the minimum number of carbons that can be there in the simplest ketone is always 3. You cannot have a ketone with 1 or 2 carbon atoms. So these three are very fairly soluble in water. And that is because they can form hydrogen bonds with water. So we have a carbonyl compound and we have water. This has a slight negative charge, slight positive charge. This hydrogen also has slight positive charge, negative and positive. This hydrogen bonding between the carbonyl compound and water molecule is possible, because of which these lower aldehydes and ketones are soluble in water. But as the size of the R group increases, the non-polar part of the molecule, non-polar part grows in size and the solubility gradually decreases. So the lower ones are soluble. As you move on to higher aldehydes and ketones, they are insoluble. But all aldehydes and ketones are soluble in organic solvents like benzene, ethers, carbon tetrachloride, etc. Okay. So, and if you talk about the odor of aldehydes and ketones, the lower aldehydes have a very pungent odor. One example can be formaldehyde. You must have smelled it because it is used to preserve biological samples. So probably in some biology lab you must have smelled that pungent odor that comes. That is formaldehyde. But as the number of carbons increases, the pungent smell gradually becomes more soft and more aromatic. So for example, if you have smelled cinnamon, that smell cinnamon has is due to cinnamaldehyde. The structure of cinnamaldehyde is this. So as the number of carbon atoms increases, the smell becomes much more pleasant. So this is it for the structure. Now we'll move on to some methods of preparation of aldehydes and ketones. The methods of preparation of aldehydes and ketones are divided into three for simplicity. One is where you study the common methods of preparation, the reactions which can be used for the preparation of both aldehydes and ketones. Then you study the reactions which are only for aldehydes or that are specific to aldehydes, the methods which are used only for the preparation of aldehydes, and then the methods which can only be used for the preparation of ketones. Okay, so first of all, let us see the methods that are common to aldehydes and ketones. Common methods of preparation. There are two methods, both of which you have already covered in alcohols and alkenes respectively. First one is dehydrogenation or oxidation. So basically in this reaction, we have an alcohol which loses a dihydrogen from here and from here to give us a carbonyl compound. So the first is dehydrogenation or oxidation of alcohols. There are two ways to dehydrogenate alcohols. One is using chromium trioxide or chromic oxide, anhydrous CrO3. So if we have a 1 degree alcohol, that is a primary alcohol like this one, CH3, CH2, OH, on reaction with CrO3, the OH bond here will break and one carbon hydrogen bond will break to give us an aldehyde, which will be CH3CHO. That means a primary alcohol on oxidation gives an aldehyde. Whereas if we have a secondary alcohol, like this one, this on reaction with CrO3 will give us a ketone, CH3, C double bond O. Alright, here this carbon hydrogen bond broke and this oxygen hydrogen bond broke to remove a molecule of dihydrogen, giving us a ketone, which is acetone in this case. So a 1 degree alcohol gives aldehyde, a 2-degree alcohol gives a ketone. Now there is another way which is the use of pyridinium chlorochromate, which is PCC. What is specific about or special about PCC, that if there is a double bond present in the alcohol, that is if we have an unsaturated alcohol, we can oxidize it to an aldehyde and leave the double bond untouched. For example, if we have this compound CH2OH here, we treat it with PCC, this double bond will not get oxidized and we will get CHO as the aldehyde or as the product. So this is one way to do oxidation or dehydrogenation. That is another method which is used for volatile alcohols. So this is oxidation of volatile alcohols. In this method, vapors of the alcohol are passed over heavy metal catalysts like copper or silver at 573 Kelvin, and just like the case in the previous reaction, 1-degree alcohols give aldehydes and 2-degree alcohols give ketones. Let us take some reaction to understand it. CH3, CH2, CH2OH here. When passed over copper at 573 Kelvin, we will get CH3, CH2, CHO, propanol. And if we have a 2-degree alcohol, CH3, CH2, CHOH, CH2, CH3 here. This when passed over copper or silver, 573 Kelvin, we will get a ketone, and this carbon here will get converted to a carbonyl carbon. So this will be CH3, CH2, C double bond O, CH2, CH3. This is a ketone right here. So these are the two methods of oxidation. The next method, which is common to the preparation of aldehydes and ketones, is through hydrocarbons. Hydration of alkynes. If you have an alkyne which has a triple bond, water will add on to it in the presence of hot dilute sulfuric acid and HgSO4 at this temperature to first give us a vinyl alcohol, which will isomerize to give us the carbonyl compound. Let us see how. So if we take the simplest, that is CH triple bond CH, ethyne, and add on a molecule of water to it, H plus HgSO4. H will get added on here, OH will get added on here. Both the carbons are the same, so there is absolutely no confusion here. So we will have CH2 double bond CHOH. Now this vinyl alcohol will isomerize to give us this compound here, which is an aldehyde. So an ethyne will give aldehyde. All other homologues of ethyne. That means apart from ethyne, all the other alkynes will give us ketones. Let us see how. We have CH3C triple bond CH. This one, okay, a propyne molecule. When it adds on a molecule of water, HOH, in the presence of acid and mercurous sulfate, what will happen here? Markovnikov's addition will take place. So OH is the negative part of the addendum, H plus is the positive part. According to the Markovnikov's rule, Markovnikov's addition will take place. The negative part of the addendum will go to the carbon having less number of hydrogens. So OH will get attached to this carbon. CH3, COH, double bond, CH2. This vinyl alcohol, this vinylic alcohol will then isomerize to give us a ketone, which is acetone in this case. So there are in all 4 common reactions. One is oxidation of alcohols using CrO3. Then we have dehydrogenation of alcohols using copper. Then we have ozonolysis of alkenes, and we have hydration of alkynes. So all of these methods give us either aldehydes or ketones depending on the method that we have used. Next set of reactions is specific for aldehydes only. Here. So the first reaction that is specific to aldehydes, reactions for aldehydes only, is Rosenmund reduction. Rosenmund reaction, which is reduction of an acid chloride. So we have an acid chloride, RCOCl here. This, when reduced, that is when hydrogen is added to it, in the presence of a palladium catalyst supported over barium sulfate, we get the aldehyde here. So RCHO is the product. Or if we have benzoyl chloride also, with hydrogen, presence of palladium, barium sulfate, we will get benzaldehyde as the product. Benzaldehyde here. What you need to know is that the aldehyde that is produced through this reduction reaction is more prone to reduction than the acyl chloride that we use in the beginning. That means the end product of this reaction should be eventually an alcohol. How do we stop the reaction so that we only get the aldehyde and it does not proceed further to give us an alcohol? For that particular reason, we use barium sulfate. Barium sulfate acts as a poison to this catalyst of palladium so that the reaction stops at the intermediate aldehyde stage and does not move further. So this is the purpose of using a palladium barium sulfate catalyst here. This is Rosenmund reduction. The next reaction is from cyanides or nitriles. This is called the Stephens method. From cyanides, Stephens method. So if we have a cyanide, this reacts with stannous chloride SnCl2 in the presence of HCl to give us an imine first, double bond and H here. This is an imine which on acidification gives us the required aldehyde. So if you look here, this R group can be either alkyl or aryl. When treated with SnCl2 and HCl, we get this imine here, which can further be hydrolyzed using an acid to the aldehyde here. What happens when we have a nitrile which has a double bond in it too? For example, this compound. CH3, C, H double bond, CH, CH2, C triple bond N here. Such a compound is reduced to an aldehyde using Debal H. This is diisobutyl aluminium hydride. So we have aluminium hydride and isobutyl 2. Using this we can do selective procedure where we will get followed by hydrolysis to give us CH3, CH double bond, CH, this bond remains unaffected, CH2, CHO. We will get the aldehyde. Debal H can also be used to reduce aldehydes, to reduce esters to aldehydes here. So we have an ester here, C double bond O, C2H5 this side. Using Debal H followed by hydrolysis, you will get this aldehyde here. Now, the next reaction is from hydrocarbons. There are multiple ways to get aldehydes from hydrocarbons. From hydrocarbons. The first one is from toluene. You oxidize toluene using two reagents. The first reagent here is chromyl chloride, Cr2, CrO2, Cl2, which is chromyl chloride. Oxidation of toluene using chromyl chloride proceeds like this: CH3, CrO2, Cl2. We use a solvent like CCl4 or CS2. Now what are we doing here? We are using a reagent which makes the methyl group here form a complex which is difficult to oxidize further. Otherwise, if we use a strong oxidizing agent, this toluene will get oxidized to a benzoic acid. So there are two reagents which stop the procedure at only aldehyde. How do they do it? Chromyl chloride forms a complex with the methyl group here so that it cannot be oxidized further and we get an aldehyde. So what do we get here? In this solvent, this is the intermediate we get. CH, O, CrOH, Cl2, O, CrOH, Cl2. This is the intermediate that we get. This one decomposed with water give us benzaldehyde. This reaction is called the Etard reaction. Now there is another way to oxidize toluene, that is using chromic oxide. The second one here is using CrO3. So if we use chromic oxide on toluene plus CrO3 with acetic anhydride, we will again get a complex intermediate like this: CH, O, CO, CH3, O, CO, CH3, which when treated with acid and water gives us benzaldehyde as the product. So these are the two methods. Now I am going to tell a few reactions which are of a little advanced level. What happens if you have metaxylene? Now metaxylene has 2 methyl groups. When such is the case and it is treated with either chromyl chloride or CrO3, only one of these methyl groups will get oxidized to the aldehyde group and we will get this product. CHO, and this one will stay as it is. So product will be 3-methyl benzaldehyde. Another thing, these methods can also be used for the preparation of ketones. How so? If we have this molecule as starting reagent, this is N-propylbenzene. When treated with CrO2, Cl2, chromyl chloride followed by hydrolysis, we will get a mixture of ketones here through rearrangement. So one would be this one, CH2, CH3, which is an ethyl phenyl ketone, and we will get this one as well. CH3, which is phenyl acetophenone. So these two reactions are not there in your book. They are a little advanced, but you need to understand, in case there is another methyl group, only one of them will get oxidized. And if instead of methyl group, we have a propyl group, a mixture of ketones would be formed. The next reaction where we can get a benzaldehyde or its derivative is using side chain chlorination of toluene. So here, side chain chlorination. We have toluene. When we treat it with Cl2 in the presence of light, that is HNu, first we will get benzyl chloride, which again on hydrolysis will give us benzaldehyde here. Okay. The third reaction is the Gattermann-Koch reaction. Gattermann-Koch reaction. What happens in the Gattermann-Koch reaction? We start with benzene or its derivative. Let us start with benzene for simplicity first. This reacts with a molecule of carbon monoxide and HCl in the presence of a Lewis acid like anhydrous AlCl3 to give us benzaldehyde. What exactly is happening in this reaction, in Gattermann-Koch reaction? Look at the reactants here apart from benzene. We have carbon monoxide, which reacts with HCl and AlCl3 to give us AlCl4 minus this complex with aluminium plus this moiety here. You see HCO moiety here with the positive charge on carbon. We can draw a resonance structure also where we get positive charges on oxygen. Now if you look at these two, the positive charge on carbon is a more stable resonance structure because the positive charge is on the more electropositive element. So this HCO moiety here acts as an electrophile, and this reaction is sort of an electrophilic addition reaction to benzene. So HCO from here gets added on to benzene to give us the product that is benzaldehyde here. Benzaldehyde. if we have a substituent on the benzene ring, for example, if we have toluene, in such a case, if we add carbon monoxide HCl, anhydrous AlCl3, the CHO group will only come at the para position. CHO. So we will get paramethyl benzaldehyde. This method is not applicable for phenols when the substituent is an OH group or ethers, or when the substituent is a highly deactivating group like NO2. So for these three groups, this reaction does not take place. Okay. So this is it for the reaction of aldehydes. Now the methods of preparation for ketones, there are three methods which are used only for the preparation of ketones. One is the Friedel-Crafts acylation reaction, which we have done multiple times. So I will not repeat it here. In Friedel-Crafts acylation reaction, we have an acid chloride like RCOCl or ArCOCl in the presence of a Lewis acid like AlCl3. This part COCl, this part gets added on to the benzene ring to give us a ketone. Right? That's Friedel-Crafts acylation. The second method is from acyl chloride and cadmium chloride. In this method, what happens is, we have cadmium chloride CdCl2. It reacts with a Grignard reagent RMgX to give us CdR2. That is a diaryl cadmium. A diaryl cadmium plus RxMg here. Okay. That's MgXCl. Now this diaryl cadmium CdR2 reacts with a molecule of acid chloride again to give us the ketone. We will have RCOR plus cadmium chloride will be regenerated. So this is how we get a ketone from an acid chloride and cadmium chloride. Cadmium chloride is first reacted with the Grignard reagent, and then the diaryl cadmium that we get is treated with an acid chloride to give us the ketone here. The third reaction is from nitriles or cyanides. So here, if we have a cyanide, it will react with a Grignard reagent like this one, C6H5MgBr, to give us an intermediate first, which can be hydrolyzed to give us the ketone. We have CH3, CH2. Let's take another example, triple bond N. This reacts with this Grignard reagent here to give us a complex which can be written like this: CH3, CH2, CH2, C, double bond here, and the phenyl group comes here, Mg, N, Mg, Br. Okay, so what is happening? To this carbon-nitrogen bond, to this carbon, the phenyl group is getting attached, and to this nitrogen, MgBr is getting attached here. This on hydrolysis gives us CH3, CH2, CH2, C. This carbon now gets the oxygen and becomes the carbonyl carbon, and the phenyl group here. So we get this ketone like this here. So these are the methods of preparation for only ketones. So in this video, we talked about aldehydes and ketones, their structure, their nomenclature, and their methods of preparation. The methods of preparation are either common to aldehydes or ketones, or they are specific. This is part 1 of the video. I'll see you next in the part 2 of the video, where we will be talking about all the chemical reactions of aldehydes and ketones. Thank you so much for watching.